All right, welcome back again, everybody. Today is the day. Today is the day we are finally going to talk about polynomials and the Weierstrass Approximation Theorem. Let me pull up the slides. Let's get started. And I hope you're in for some exciting stuff because this is some of the coolest stuff, I think. All right, here we go. So Section 3.5, we're kind of in the middle of this chapter on polynomials and rational functions. This one's all about polynomials and a very important and very famous theorem called the Weierstrass Approximation Theorem, or more generally, the Stone-Weierstrass Approximation Theorem. So here's the overview for the section. We're just going to talk about what polynomial functions are. We're going to define them, define the degree of a polynomial. Then we're going to talk about the Weierstrass Approximation Theorem. I will give you an example of it. You'll actually see another example in the activity for this section, and you will see many, many examples in Calculus 2. We'll talk about power functions, which are kind of the building blocks of polynomials. They're essentially just functions that have larger exponents, that's all. We'll talk about graphing power functions using transformations. We'll talk about the factor theorem, which is a generalization of a theorem that we saw earlier on in this chapter. Then we're going to split things up into local behavior and global behavior, kind of like we did in one of the previous chapters. We're going to talk about real zeros, that is, zeros of polynomials that are real numbers. We're going to talk about turning points. Then we're going to talk about global behavior, talking about the way these polynomials behave at plus or minus infinity. And to do that, we're going to have to introduce a very important function called the limit operator. And you're going to be working with this operator forevermore, I'll just say, especially in Calc 1, 2, and 3. This is one of the fundamental tools of those courses, the limit operator. Then we're going to do one example at the end where we can determine a polynomial function just by looking at the graph, at least up to multiplicity of the zeros, you could say. All right, let's get started. So first, what is a polynomial function? There's a lot to define, so we're going to do this slowly, but we'll keep it simple to begin with. So a function p is called a polynomial if it has this standard form right here. Now, don't worry, your eyes might be glazing over looking at all this notation. It's just a way of being very generic and also being very precise. So let me kind of point out the structure here, and then I'll read the following paragraph. Notice that there's a whole bunch of terms here. Okay, so just focus on the terms, the things that are separated by those plus signs, right? So you've got this term, you've got this term, you've got this term, this term here, right? So what's happening here is you're basically taking these higher powers of x and you're possibly multiplying those higher powers by these coefficients right here, just like so. And that's really what it is. You're just adding up a bunch of those. So each one of these little things here, these coefficients, a sub n minus 1, a sub 2, a sub 1, a sub 0, those are all just real numbers for now, okay? Pretend they're real numbers. And then what you're doing is you're multiplying these power functions, x to the n, x to the n minus 1, x squared, x, and there could be a whole bunch of stuff going on in between, but it's going to keep that same pattern. The reason that this is an n is because we don't know what the largest power is necessarily going to be. So n here could be any positive integer. N could be 1,000,000 if you want. And then this would be 1,000,000 minus 1, 1,000,000 minus 2, 1,000,000 minus 3, dot, 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 until you get all the way down to 2, and then 1. And then this is actually, you could think of it as times x to the 0, because anything to the 0 is 1. So a polynomial is basically just a sum of a bunch of these things, just like that, okay? So let's go through some of the details. N has got to be a non-negative integer, so it's got to be 0, 1, 2, 3, 4, 5, or anything above. These numbers here, that should actually say A0. A0, those are constants, and they're called the coefficients of the polynomial. If a sub n is not 0, then a sub n is called the leading coefficient. That's just the number that's in the front, and it's associated with the highest power. The degree of the polynomial is the highest power. So when you look at this, if you've got a polynomial, the degree is the highest power that you see when it's written in this form right here, the exponent of the leading term. This is also what we call the leading term, just like this. is the leading coefficient. So here's an example of a polynomial of degree 6. And we're just going to look at it piece by piece. So the reason it's degree 6 is because the highest power present is a 6. So it's a degree 6 polynomial. But notice that it's really just a sum or a difference of a bunch of those what are called power functions. 2 times x to the 6th minus x to the 4th plus 2/5 x cubed plus square root of 2. The coefficients, the numbers involved here could be real numbers. Right now we're just focusing on real numbers, and then we're going to generalize this after the next section when we talk about complex numbers. All right, so here's an example of a polynomial. We're going to see a bunch more. One important note here at the bottom, the domain of any polynomial is all real numbers, okay? So polynomials are really, really nice in that respect. You can plug any real number you want into a polynomial and it'll work. Those things can chew up any number you give them. Right. So here is a good exercise. The question is, which of the following are polynomials? And for those that are polynomials, what's their degree? So I want you to try this one on your own, but before you do, you might want to refresh your memory about this definition and maybe take a look at this example. Uh, yeah, I'll just leave it at that and I'll let you kind of mess around with it. So first, ponder it for a minute, kind of take a look. Then, like always, you got to say something out loud. Say it to your dog, say it to your cat, say it to yourself, just anything out loud to get your brain thinking about what you're going to do. Okay, now try to write it out. See if you can determine which of those are polynomials, and if they are a polynomial, what's the degree? Right, here we go. So first off, this one is definitely a polynomial. It's got that structure, and the degree here is going to be 3. That is the highest power that you see in that expression. Number 2 is also a polynomial, and it's of degree 4. It's just now the terms are not written in the same order. That's okay. The terms can be mixed around. As long as you have something that can be represented in this way, it will be a polynomial. 3 actually is not a polynomial. This is a radical function. It's a square root function. Maybe more accurately, we'll talk more about this in chapter 4, even though we've seen it a couple of times. We could rewrite this as x to the 1/2. So here, this power, this exponent, is not a positive integer or not a non-negative integer, so this can't be a polynomial. This one is also not a polynomial. This is actually what we call a rational function. And this is what we're going to spend the last 2 sections of this chapter focusing on, rational functions. But it's not a polynomial. So that's that. This one, this one is a little bit deceptive. This one is a polynomial. It's just a very simple polynomial. It's a constant function. This is a situation where the degree of the polynomial is actually 0. So how do you see that? Well, you could interpret this, oops, as 8x to the 0. Remember, anything to the 0, except for 0, is 1. So 8x to the 0 is 8. So what that means is any constant function is automatically a polynomial. Moreover, any linear function is a polynomial. Any quadratic function is a polynomial. Any cubic function is a polynomial. All of these things are polynomials, all right? Just like simple versions of them that don't have a high degree. Now, here's another one that's a little bit deceptive. This one is also a polynomial. And the reason for that is if you were to multiply everything out, you would be able to write it in the standard form that you see right here. You can write it in standard form. You would just have to multiply this and then distribute this to all of those terms and so on and so on. And then you could write it in standard form. This is actually what we call the factored form of the polynomial. So maybe that'll sound kind of familiar from when we were talking about quadratic functions. You're going to notice a lot of familiarity with what we were talking about before, because now we're generalizing these things. Okay. So some attributes of polynomials. So for one, polynomials are continuous and they are smooth. So what that means is there aren't any gaps. So if you've got gaps, then you don't have a polynomial. They are also smooth, which means that there aren't any corners, cusps, or kinks. I've got some examples here. Here you've got a corner. That corner makes the graph not a polynomial, not the graph of a polynomial. This gap, this discontinuity you see there, that makes it not a polynomial. This is what we call a cusp. It's kind of a sharp needle point. That also is not a polynomial. That's what makes it not a polynomial. So when you think of polynomials, we really are talking about functions that look like this over here. Very smooth, continuous, a little bit wavy, right? So they kind of look like this. But some graphs also look smooth and continuous, but they're not polynomials. And that's why we need the algebraic definition, the one that we gave right at the beginning. Polynomials have to be written or have to be able to be written in this form. All right. Okay. So we've spent a lot of time building up to this, and we're going to spend a lot of time talking about polynomials over the next few sections. And you're going to see them a lot in the future in the calculus sequence, in your STEM career. Big question is, why do we care? Remember, you got to remember to ask those big questions. Why do we care? Who cares? Why are we studying all this stuff about polynomials? Why are we investing all this time? Why are we learning about factoring quadratics and factoring polynomials? What's the whole point? Well, I think that a really great motivation for the study of polynomials is this, the Weierstrass Approximation Theorem. And this is one of the ways it can be stated. I mentioned this before, but I'm going to elaborate on it today. We're going to see an example of it in just a moment. But here is what that theorem says. Suppose that f is a continuous real-valued function defined on a closed interval a to b. Then, for every epsilon greater than 0, there exists a polynomial p such that for every point in that interval a to b, we have the distance between the function and the polynomial is less than epsilon. All right? So here's one where I want you to just kind of ponder that for a minute. So stare at that theorem for just a minute. Okay, now I want you to try to maybe say it in your own words. If you want, you can kind of take a peek down here, but see if you could just say it in your own words so that it kind of clicks in your brain. Right. Now, let's elaborate on this. This type of expression here, this inequality, is something that we've seen before. We saw this back in chapter 1 when we first started talking about the theory of approximation. And that was to help you get ready to understand this statement and understand even more when you get into the calculus sequence. Really, what this is saying is something very, very powerful. If your function is continuous on a closed interval, then we can find a polynomial that approximates your function as close as you want. So if you remember from chapter 1, epsilon is what we often call a tolerance or an error. It's basically how far off things are allowed to be, right? So epsilon is like, oh, we're okay with an error of zero point 0.1, zero point 0.01, zero point 0.001. And what this theorem says is no matter what this function is, whatever that function is, as long as it's continuous on that closed interval, then we can find a function, p of x, that approximates that polynomial, I'm sorry, approximates that function within the tolerance that you specify. All right. Now, yeah, basically this right here, uniformly and arbitrarily closely, that means it's true for every x in that interval. That's what uniformly means. And arbitrarily closely means for any epsilon. So whatever tolerance you give us, we can find a polynomial that will approximate your function within that tolerance, okay? So yeah, what is the utility of this? Well, in essence, we can use a much nicer type of function for our analysis in place of what might be called a highly pathological function. That means it's sick. The function is just gross, it's messy, it's hard to work with. Well, if we can avoid that, we would like to avoid it, right? We don't want to have to work with these things that are really difficult to deal with. So, as long as we're okay with a small error, epsilon, we could instead pass to a polynomial. We just got to remember that there's a small error associated with any result we get. But polynomials are just such nice functions. They're really nice. I mean, we're going to see linear combinations of power functions. They're factorable. There's a relationship between the factors and the zeros, just like we saw with quadratic functions. So if we could, we would really like to be able to just use a polynomial. But not every situation gives rise to a polynomial. Our function might just be continuous on a closed interval, but This theorem says we could just use a polynomial as long as we're okay with a tiny bit of error, however small you want the error to be, okay? So maybe speaking to technology a little bit, this is extremely helpful because computers are excellent at producing, factoring, and generally working with polynomials. We're going to see that in this chapter in sections 3.7, 3.8, and 3.9. So this is one of the reasons that we dwell on polynomials in a pre-calculus level course. They're a fundamental tool of math and science. Um, here's another little precursor, maybe some foreshadowing. Many of you are going to have to take calculus 2. It's a difficult class, but you learn some really incredible stuff in there. In particular, you're going to learn about what are called Taylor series. And Taylor series are literally a way of approximating I'm sorry, are a way of creating polynomials that approximate functions. That's really what they are for. So in Calc 2, you're going to learn how to do that. You're going to be able to approximate functions that are sufficiently smooth using polynomials. So for example, if we're near the point x equals 0, we can approximate the sine function by this polynomial, that polynomial right there. So let me pause here and give some disclaimers for a minute. One, we're going to study the sine function in detail in chapter 6 when we get to trigonometry. Two, just because we can find a polynomial that approximates the function as close as we want, that doesn't mean the polynomial is going to look pretty, right? These coefficients can get pretty gnarly. The coefficients can be all sorts of weird, irrational numbers or whatever, but they still have the structure of a polynomial. All right, that's the big takeaway. So what you're looking at here, this is actually what we call the ninth order polynomial approximation of sine of x near 0. Ninth order because the degree is 9, and this is actually exact to 7 decimal places. So what that means is if you need to work with the sine function near the point x equals 0, you could instead just work with this polynomial, and your results would be accurate up to 7 decimal places, right? So that's really, really nice. Maybe what might be more surprising is physicists, when they work with the sine function very near 0, they actually just use the first order or the linear approximation sine of x equals x. That's right. So this is a real thing that happens in physics. You'll often see physicists take this and just swap it out for x. Well, you're allowed to do that as long as you are applying the Weierstrass Approximation Theorem. So what this means is when x is very close to 0, this approximation is good enough for a lot of applications, right? That's the power of this theorem. Okay, let's see it in action real quick. So let's approximate the function absolute value of x at 0 with a polynomial. Now remember what the absolute value function looks like. It looks like, that v, that is not a polynomial because it's got a corner, right? But the Weierstrass approximation theorem says there exists a polynomial that will approximate that corner, that function, as close as you want. And we're going to see it right now, okay? Let me pull up the slides, or sorry, let me pull up this Desmos example, and we'll take a look. You can follow along yourself if you want to mess around with it. All right, here we go. There it is. All right. So, quick thing, like I had mentioned before, just because we can find the polynomial, that doesn't mean that the polynomial looks nice, okay? This might make your eyes kind of glaze over. That's okay. If it makes you feel any better, this is something that you will learn about in Calculus 2 or by Calculus 2. What we're going to explore in this class are series or summations. We'll talk about combinations. Some of you may have seen this symbol before. And what we're doing here is we're basically adding up a bunch of these things. All right. So here, let me do this first. Here's the absolute value function, right? Here's the absolute value function, just like that. And now this is basically a polynomial written in closed form using sigma notation or summation notation. K here is basically the degree of the polynomial. Oh, I'm sorry. N here is the degree of the polynomial. And then what we're going to do is we're going to add up a bunch of these terms that look like this. The terms are messy, but watch what function or watch what graph it produces. Let's make the degree, well, see, the degree is 0 right now. Degree 0, constant function. Let's do degree 1. Oops, too fast. Degree 1. There we go. Okay, now moving on, we're going to go up. Now take a look at this red curve. You see this red curve? Maybe I'll actually make this blue. There we go. We're going to make this blue and that one's red. Okay, so that red function you see, that is a polynomial. That's a polynomial right there. All right. Now we're going to keep going. This one's actually degree 4. 2 times 2 gives us 4. And we're going to keep going. And I want you to watch what happens with this little curvy thing and this corner. So we're going to increase n. There it goes. There it goes. Look at that. So this red curve that you see, that's a polynomial. That's a polynomial of degree 34. 2 times 17 gives us 34. And look, it's almost perfectly coinciding with the absolute value function on this interval, right? The interval where this is valid is actually negative square root of 2 to square root of 2. But look, see, right here, it's getting close to approximating that point. Let's increase the degree even more. Ooh, you see? This is the Weierstrass Approximation Theorem in action. What it's saying is, hey, guess what? This function, the absolute value function, if you don't want to work with it, you could instead work with this polynomial of degree 166, and it'll be okay. It'll get you what you need as long as you're okay with a little bit of error. The little bit of error is the distance between this point and this point, right? At 0, absolute value of x is equal to 0, but this function at 0 is equal to 0.061835. So there's an error associated with this polynomial approximation. And that error is basically this amount. It's the difference between 0 and this number, right? That is what the Weierstrass approximation theorem says. So let me flash back for just a moment here. Let me flash back for just a moment to the slides. Okay, look at this. Look at this algebraic expression here, this inequality. F of x for us is absolute value of x. P of x is that red polynomial curve you're seeing, and epsilon is that space. It's that space between the absolute value function and the polynomial right here. So this distance right here is basically epsilon, the maximum that the functions will differ, right? The maximum amount, the maximum size that the functions will differ. All right, zooming back out. Ooh, oh, dude, I'm Desmos is having trouble calculating this. That's why if you see, like when I zoom out, it takes it some time to fill in the gaps. We're asking the computer to do a lot of work by computing all of this stuff. Again, that's a polynomial of degree 166. Maybe I could go even farther up. Ooh, let's go to 100. Desmos is really struggling here, but there we go. There we go. See, tiny bit more accuracy. Tiny bit more accuracy. Oh, there we go. There we go. But that's it. That's the Weierstrass approximation theorem. That's why it's so powerful. That's why we study polynomials, and that's why we talk about it now in this class. All right. So that being said, let's talk about what power functions are. Let's back up for just a minute. Let me drop that degree down to 0 again. Save my computer a little bit of processing power. Um, so what is a power function? So a power function is just a function of this form, a times x to the n, where a is a real number and n greater than 0 or equal to 0, sorry, should say n greater than or equal to 0 is an integer. All right. So we're basically looking at powers of x, integer powers of x. And the shape of the graph depends on the value of n. So I've got another Desmos example here. 1 second. Do this. Okay, let me see if I can pull it up. Do I have it set up already? I do. Perfect. Okay, so let's take a look at some power functions. I forgot to include a. There we go. Forgot to include a. So when n is 0, just like before, you've just got a constant function crossing at 1, right? Anything to the 0 is 1. Now, as we increase the degree, when n is 1, we get a times x. Right now, a is just 1. When we increase the degree, we get the identity function, f of x equals x. When the degree is 2, you get a quadratic, you get a parabola, right? When it's 3, you get a cubic function. These are graphs that you've seen in the past. Now let's continue to increase the degree. When n is 4, 5, 6, wait, 5, 6, 7, 8, 9, 10, 11, 12. Let's just keep going up. So you can see the behavior of these graphs. So notice what's happening as n gets larger and larger. For one, if n is even, then the graph basically looks like a flattened out parabola, right? This area right here, flattened out. Oop, flattened out. When n is odd, it looks like a flattened out cubic function. That's basically the idea. So the greater the degree, the more eccentric the graph gets when you're in the interval -1 to 1. But it still roughly resembles those lower order power functions, x squared and x cubed, or just x if the degree is 1, right? You'll get to explore that on the homework, and we're going to talk about it in a minute. But this is what those power functions look like. Okay, now as a corollary, we get this. Polynomials are what we call linear combinations of power functions. So what you can imagine is adding up a bunch of those graphs. Add up a bunch of graphs that look like this. And when you do that, you get a polynomial. That's one of the reasons we studied that graphical arithmetic that we did back in chapter 2 when we were messing with functions. And in the activity, you actually did graphical arithmetic to produce a polynomial from two power functions, right? So a polynomial is just a linear combination. It means adding up a bunch of these things. Basically, add up a bunch of power functions and you get a polynomial. The reason that I'm introducing this now is because you're going to explore that in much greater detail when you get to linear algebra. There's some really deep math associated with the construction of these polynomials. Okay, let's look at some properties of this power function. So I kind of mentioned some of this. When the power is even, then f is an even function, so it's symmetric about the y-axis, right? The domain is -infinity to infinity. No problem with any numbers here. Now, when the power is even, the range is 0 to infinity. So let me go back to this for a sec so you can see. Here we go. Right? So when the degree is even, right now it's 36, the range is 0 and up. All right? Even degree. The graph always passes through these points. So as long as you're not stretching using A or shifting it around, the graph will always pass through these 3 points. Let's take a look. Right? So here, n is 36, but notice it still passes through the point. Hey, where is it? -1, 1, 1, 1, and 0, 0. So that will always be the case unless you start moving things around. If you start changing this leading coefficient, you can do stretches and squishes, right? If you start shifting things around. But when you're just looking at something of this form, it's always going to pass through those 3 points when n is even, right? Now, when n increases, the graph is steeper when x is less than -1 or greater than 1. And again, you can see that in that Desmos example, right? So as long as we are away from -1, the graph is very steep. Or I should say, when we're near -1 and near 1, the graph is very steep. But it gets shallower. Wait, go back. There it is. It gets shallower when you're between -1 and 1. That's the flattening out that you notice in that example there, right? The flattening out. And that makes sense if you appeal to our fundamental intuition we talked about in chapter 1, right? We're raising the power, so that means we're multiplying more times, right? So this is whatever number x multiplied by itself 36 times. Well, if the size of x is small, if it's like 1/2, 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2, 36 times, you're going to get a very small number. That's why it's so low, right? It's not very large. But when x is bigger, when x is a bigger number, like maybe x is 2, now you're doing 2 to the 36. That's 2 times 2 times 2 times 2 times 2 times 2 times 2. That's huge. That's a very, very big number. In fact, we could even calculate it right here. Look, what is f of 2? 6.8719476736 times 10 to the 10. This is why it's important to talk about scientific notation because these numbers can get large pretty quickly. So I don't want to have to write out all those decimal places. I'd rather write out some of these and just say times 10 to the 10, right? what is that? 10 to the 10. I think a 10 to the 9 is a billion. So this is 10 billions. There you go. 6.8, 10 billions. All right. Now, let's compare that to when the power is odd. So when n is odd, the graph is similar, but it's going to behave very much like x cubed, right? Instead of x squared, it's going to be like x cubed. I'll prepare this one. Let's make it degree 37. Okay, and then back to this. So when f is odd, it's symmetric about the origin. So when this power is odd, it's symmetric about the origin. Domain is still negative infinity to infinity. Now the range is negative infinity to infinity because when you raise something to an odd power, negatives are preserved. So let me flash over to the graph for a minute. You see here, we're okay with negative numbers. We can get negative results when the degree is odd, right? When that power is odd. There we go. Just like so. All right. The graph still passes through some common points. It passes through 1, 1, 0, 0, and now negative 1 instead of negative 1, 1. So let me go show you on that. Here we go. Now this is passing through negative 1, 0, 0, and 1, 1. Yep, 1, 1, just like so. The difference between this one and one where the power is even is that this point is actually up here, right? So let me go back to the slides and I'll kind of flash back and forth. There you go. I did it on purpose so that way you could kind of flick back and forth between these. There you go. Now, just as it was with an even function, when x is greater than negative 1, I'm sorry, less than negative 1 or greater than 1, the graph gets steeper very fast. And when you're between negative 1 and 1, the graph gets shallower very fast. It gets compressed, right? For the same reasons I gave before, just use your fundamental intuition. You're multiplying more times. If your number is less than 1 in size, then the result is going to shrink rapidly. If your number is bigger than 1 in size, your result is going to grow rapidly. And that's the basic idea. Okay, good news is we can graph these things using transformations, and you already have lots of experience doing this before. So everything that we talked about in chapter 2, everything we talked about in regard to parabolas and shifting those things around, all of that applies to power functions. So here's one that I want you to try on your own. I want you to try to graph this function using transformations, okay? So think about it for a minute, right? Now, say something out loud about maybe what you would try, or what would you do first? And now, try to work it out. Use what you know from the previous chapters and try to graph that function. And we'll do it together in a moment. Right, here we go. So this is x to the 7th, but the first thing we're doing to x to the 7th is we're reflecting it vertically by that negative, right? And then we're going to shift it vertically upward 2 units. So we've got two transformations. We're taking x to the 7th, flipping it vertically, and then shifting it vertically. Here we go. So here's the original graph. I may need to do this to zoom in on it. Hold on. Here we go. There we go. Hey, 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 come back. Okay, so here's the original graph, x to the 7th. Now we're going to reflect it vertically. And remember, when we do that, all of the outputs change sign. So this point's going to move down here, that one's going to move here, 0 is going to stay exactly where it is, and that's what you get, just like that. Now we're going to take that graph and we're just going to shift it up by 2 units. So take this graph and pull it up by 2 units, and this is what you get right here. There you go. There's the shift up 2 units. You can follow where the points go. So this was the point negative 1, 1. Now it's negative 1, 3 because it's been shifted up by 2, right? It basically went up 2 units. And this one went up 2 units. Oops, too far. Just like that. So all that's the same. It's just now the graph looks a little more eccentric. I'll just say that. Okay, let's do one more example. One more example, you'll get some more practice on the homework as well. Try to graph this function using transformations. This is another power function. Think about it for a minute. Okay, say something out loud. Maybe what you'll do first, maybe what the first transformation is. And now try to graph that on your own. Graph this function using transformations. Like draw the picture. Okay. All right, now let's do it together. Here we've got the parent function here is just x to the sixth, but we're going to shift it horizontally to the left by 1 unit, and then we're going to vertically stretch it by a factor of 2. So those are the two transformations involved here. Here is the original function. Let me zoom in a bit here. There we go. Here's the original function, x to the sixth. Again, because this power is even, it looks like x squared, but it's just flatter in the middle, right? Flatter in the middle and stretchier on the outsides. So this is the original function, x to the sixth, the parent function. Now we're going to shift it to the left by 1 unit. There we go. So this point went over by 1, this point went over by 1, and that's why we have these points here. Okay, now we're going to vertically stretch it. So this number is bigger than 1, so it's going to stretch it vertically. So every one of these points that's not a 0 is going to stretch by a factor of 2, just like this. Boom, you see how it's like stretchier now? And that's all it is. So everything you learned in the past when we were doing this back in chapter 2 still applies. It's the same idea, right? This was a 1, multiply 1 by 2, and you get 2. This was a 1, multiply 1 by 2, and you get 2. 0 times 2 is 0, no change there. And every other point is getting stretched by a factor of 2, every other point. Okay, now let me go back to these ones. There we go. Oop, there we go. Okay, so now that we've got an idea of the basics of a polynomial, why we're studying them, we've talked about power functions, let's start getting some really important theorems, and we're going to leverage these theorems. So one thing I got to remind you about is the definition of a zero of a function or the root of an equation. So if we're given a function f, if there is an input r such that f of r equals 0, then we call r a zero of the function or a root of that function equation, a root of that equation right there. So we've talked about this a lot, right? And we were talking about root finding problems a lot, and we're still going to because of this really powerful theorem called the factor theorem. This again is kind of like why we care about polynomials. So the factor theorem says this: the following statements are equivalent, meaning they all imply each other in all directions. So if you've got one of them, you've got all of them, okay? So first, r is a zero of a polynomial, x minus r is a factor of f of x. And if r is a real number, then r is an x-intercept of the graph of f. So all of these statements are equivalent, which means they all imply each other. So this implies this, which implies this. This implies this. This implies this. This implies this. They all imply each other. They are equivalent statements. So when we say, hey, r is a zero of a polynomial, you know immediately x minus r is a factor of that polynomial. And if r is a real number, then that 0 has to be an x-intercept. This is just, it's an incredibly powerful result. This establishes the connection between zeros of the polynomial and the linear factors of a polynomial. It's very, very powerful. This is literally a generalization of a corollary that we saw in the previous section. Was it 3.4? Think it was 3.4 or 3.3. Remember that one result we had, that important property of parabolas? And then as a corollary, we got that if you knew two zeros of the parabola, then you immediately got the factored form. That's what this says. Except now it's generalized to not just parabolas, not just quadratic functions, but polynomials in general. So there's a relationship between the factors of a polynomial and the zeros of the polynomial. And if those zeros are real, then you get x-intercepts. That's what's so amazing about this. This is basically what I'm just saying right here. Pretty much the same thing. So this theorem actually follows from something called the remainder theorem, which we're going to prove in section 3.7. We need to know a little bit about complex zeros of polynomials before we can prove the remainder theorem in general. So we're gonna hold off until 3.7 to prove, or so I should say to prove the remainder theorem from which the factor theorem follows. All right. Okay, Now, this example is going to look kind of familiar, so I do want you to try it on your own. You should be able to do it. It is very similar to what we did before. So I want you to try to find a polynomial function of degree 3 whose zeros are -3, 2, and 5, and also passes through the point 0, comma 60. Okay? So ponder that for a second, right? Now, say something out loud to yourself or to your dog or to your cat. And now try to work it out. Remember the factor theorem. If you know a zero, then you know a factor. Right. Okay, so like I was just saying a moment ago, if you know a zero, then you know a factor. So we know these zeros, so automatically we get three factors: x plus 3, x minus 2, x minus 5. The one thing we don't know, just like we didn't know before, is that leading coefficient. So right away, we can write this. Remember, there's this leading coefficient here when we talk about these factored forms. We know these have to be zeros, but we don't know what A is yet. And that is why you need an additional data point. You need a point that is not a zero of the function in order to determine this other bit of information, the leading coefficient. So that's what we're going to use. That's what we're going to use. We're going to plug in the point 0, comma 60 for our function and then solve for a. Here we go. 60 equals a times 0 plus 3, 0 minus 2, 0 minus 5. Simplify this. You get 3 times -2 times -5, which is 30. Divide both sides by 30, and you get a equals 2. And boom, there it is. That is the polynomial. Oh, another thing, you can leave it in this form. So just like I've said a few times now, this is a valid form of a polynomial. It doesn't have to be written in standard form, but the standard form exists. If you were to multiply this all out, you could get it written in standard form. That's not always required, and often, well, not always desired, I'll say. And that's going to lead us to talk about local behavior. So kind of like we saw before, the difference between a factored form of a function and a standard form of a function gives us different information about the function. So when we want to look at local behavior, the factored form is actually more beneficial because when we have the factored form, we can see a lot. We can already see the zeros. We can tell, we'll talk about global behavior in a minute, but we can tell a lot just from this factored form, local behavior. So let's talk about repeated zeros. So if we have a factor, x minus r, and it occurs more than once, so maybe there's like a power of 2 or 3 or 4, then r is what we call a repeated zero or a repeated root of p. All right. If the factor x minus r occurs exactly m many times, then we say the multiplicity of the root r, or the factor x minus r, is m. So you can think of m as the exponent associated with a factor, and that's the multiplicity of that factor. Okay. So once again, exponents are counting factors, and they're telling us how many times those factors occur. Does that sound familiar? Right? Very similar to when we were talking about, factoring integers, right? Mm, there's an interesting connection there coming up. All right, so here's one I want you to try. I want you to look at this polynomial, and I want you to tell me what are the zeros and what are the multiplicities of the zeros. Okay? So think about it for a sec. All right, maybe say something out loud. Maybe what are the zeros? See if you can just say what the zeros are out loud. Okay, now can write it. Try to write it and work it out on your own. Write down the zeros and the multiplicities. Okay. All right. So the good thing is we have the factored form. So right away we can see that 0 is a 0, -2 is a 0, and 1/4 is a 0. That's it. We can see though that's what it is immediately. The multiplicity of the 0, 0 is 2. The multiplicity of -2 is 1. And the multiplicity of 1/4 is 4, just like that, right? And then here it is just typed out. So that's what we mean by multiplicity, okay? All right, let's try this again, but let's elaborate a little bit more. There's this polynomial. I'm giving you this polynomial here. I want you to find the x and y intercepts of the graph. Then I want you to use the x-intercepts to find the intervals on which the graph of f is above or below the x-axis. Hopefully this rings a bell. Then just locate a couple of other points on the graph and connect them to draw the polynomial, all right? So ponder this for a minute, okay? Now say something out loud and work it out on your own, and we'll do it together in a moment. Okay. All right, here we go. So x and y intercepts, I can see the x-intercepts immediately. X-intercept -1 and 2. Boom. If I wanted to find the y-intercept, well, that's just when x equals 0. So if I plug 0 in for x, I can find the y-intercept. I've got that worked out right here. So wait, did I do the y-intercept first? Yeah, I just wrote it in a different order. Here's the y-intercept, -2. The zeros are -1 and 2, and the multiplicities are 2 and 1, respectively. Now, we want to figure out where this graph is above or below the x-axis. And if you remember what we did back in, oh geez, maybe section 2.6, that was when we first started talking about root finding problems and creating a sign diagram. You're going to do the same thing here. And you're going to do this a lot, even in Calc 1 and Calc 2 and Calc 3. You're going to do this, what's called a sign analysis by making a diagram. So we're going to draw a number line here that represents the x-axis. We're going to plot our zeros on that x-axis, and then we're just going to test points around those zeros. So pick an easy point less than -1. How about -2? When we plug -2 into our function as an input, we get -4, which is negative. So this is telling us that the graph lies below the x-axis, all right? The graph lies below the x-axis on this interval right here, like so. Now we're going to test another point in between -1 and 2. Good point to test is 0. So when we plug in 0, well, we already know what that is, right? That was -2. So we've got -2 here. So the graph is below the x-axis still. That's okay. That's totally allowed. Now let's plug in the number 3. And when we plug in the number 3, we get 16, which is positive. So the graph is going to be above the x-axis on this interval right here. And that's about it. Now we know it's a polynomial. We actually know what its degree is because we can just add up the multiplicities. And now we can graph it. Here it is. There it is. Yes. Let me zoom in just a tiny bit. So remember what we found with our sign analysis was that the graph was below the below the x-axis over here. And that's why you'll see down here that the graph is actually below. And then what happens is right at that 0, the graph just touches and then bounces back down. It doesn't cross the x-axis. It just goes boom and stays below. Now it's got to come back up because we know there's a 0 here at 2. And then when we tested the points over here, I think we tested 3, right? Yeah, we tested the point 3 and we got a positive number. So here the graph is crossing the x-axis and continuing upward just like that, okay? Now, there's a reason that we're getting this type of result. There's a reason that we're getting this bounce and that we're getting this crossing behavior, right? And I want to go show you the polynomial again. Here's the one that we started with. Here's the one we started with. One thing I mentioned that we'll see more. I know it's going to be degree 3 because this is a 2 and this is a 1. So that means, oh, and these are all, these are all linear factors. So that means the degree has got to be 3, right? Now, notice the multiplicity of -1 was 2, and the multiplicity of -2 was 1. Now look at this graph. Multiplicity 2, multiplicity 1. Okay? Now, ponder that for a minute while we talk about this proposition. So if we've got a polynomial function and we've got a 0 r, if the multiplicity is even, then the sign of f of x doesn't change from one side of the zero to the other. So the graph of f touches the x-axis, but does not cross it. It just kind of bounces off either that way or that way when the multiplicity is even, okay? If you've got a real zero r and the multiplicity is odd, then the sign of f of x does change from one side of r to the other. So the graph of f will cross the x-axis at r. That is exactly what we saw here. Even multiplicity, it bounced off. Odd multiplicity, it crossed. Oops, it crossed. And that's true for any zero, any linear factor of a polynomial. All right. So what's the big idea? The big idea is that if you want to know what the graph looks like, roughly speaking, well, if the multiplicity of the root is even, then the graph will look like plus or minus x squared there. It's either going to look like a parabola, maybe squished, right? It'll look like it opens up or opens down when you're near that point, when you're near that point. If the multiplicity is odd, then it's either going to look like plus or minus x, right? Just the diagonal, or plus or minus x cubed. So in other words, the multiplicity is telling you the local behavior at that point. It's either going to bounce or it's going to cross, one of those two. I've got that shown right here. Let me zoom in a bit. Okay. So I'm being very hand wavy when I say looks like, looks like. And what I'm really trying to say is it's going to bounce or it's going to cross. So here, the multiplicity on that from that previous example, for this root, it was even. And that's why it kind of bounces off. It looks like x squared. It's not equal to x squared, but it kind of looks like x squared, negative in this case because it's opening downward. And then here, the multiplicity was 1, and that's why it looks like just the diagonal, right? Just looks like. It's not that it's equal to it, but it looks like it. So this gives you a lot of intuition for what the graph looks like when you have the factored form. It tells us all about that local behavior, local behavior. That's why the factored form is nice, okay? Now, let's talk about another characteristic of local behavior, something called turning points. So the points at which a graph changes direction, those are called turning points. And at each turning point, the graph will have a local maximum or a local minimum, right? So here's an example of a bunch of turning points. This is a polynomial. You've got a turning point here, a turning point here, and a turning point here. And those are actually where the local mins and maxes are. That's what's happening at those turning points. This is actually another motivation for studying calculus because when you get into Calc 1, you will be able to locate exactly where those points are analytically, basically using algebra and using calculus to locate the exact position, the exact points of those turning points. All right, that's what you're building up to in Calc 1. Right. Okay, so now that we've seen what turning points are, we get some interesting properties related to those things. If f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points, okay? At most. It doesn't mean that it has exactly n minus 1 turning points. It just means that it could have as many as n minus 1 turning points, all right? Moreover, if the graph of a polynomial function has n minus 1 turning points, like if you can see n minus 1 turning points, then the degree of f is at least n. At least n. So let me go back to this example here. When I look at this graph, I can see 1, 2, 3. So there are 3 turning points, which means the degree of this polynomial is at least 4. One more, right? So there's 3 here. That means the degree has to be at least 4. It could be more. It could be 6 or 8 or 20 or 22, but it has to be at least 4. That's what these two propositions say. Okay. All right. Now, you might have noticed a second ago when I was talking about the degree of this particular polynomial, I was only using even numbers, 4, 6, 8, 10. There's a reason for that, and that is related to the global behavior of a polynomial. So now we need to talk about limits at plus or minus infinity, and we need to talk about the end behavior of a polynomial, okay? So the, oh, hold on one second, lost my train of thought. Da, 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 da. the behavior. Oh, yeah, there we go. Obviously, the behavior of the graph of a function for large values of x, either positive or negative, is called the end behavior. It's just what's happening at the ends of the function, all right? That's what we're going to study right now. And this is the important proposition related to the global behavior of these polynomials. So let's say we've got a polynomial here in standard form. I know this is that very general form, but remember, take a deep breath. It's just a sum of a bunch of things that look like number times x to a power plus number times x to a power plus number times x to a power, and then maybe plus a number at the end to give you a vertical shift. So the end behavior of this guy right here is the same as that of this power function. In other words, the end behavior of the polynomial is the same as the end behavior of the leading term right there, okay? That's what this is saying. So if you want to know what the end behavior is going to look like, what the behavior is going to look like roughly, it's going to look like whatever that is, okay? We're talking about way out at plus or minus infinity, okay? We're talking about huge values of x, either positive or negative, right? Gigantic value. X is like 20 quadrillion, badrillion, huge, right? What does it look like when you're way out there? It's going to look like this. Now, there's a reason for that. So first, what we call this connection is asymptotic equivalence, and we're going to talk about that a lot more in section 3.9. But what we're saying is the polynomial is asymptotically equivalent to its leading term, and we call that leading term the dominating term. And it's called the dominating term because for very large values of x, way out there, this term is huge. It's gigantic, and it dwarfs all the other terms in relative size. All right. So these powers can be whatever, but this power here, that's going to dominate the behavior when x is very, very large. So we call this the dominating term when we're speaking of a global behavior and behavior of a polynomial. Okay. Now, because we want to talk about this end behavior a little more precisely, I want to introduce you to the limit operator. You're going to explore this operator a lot in Calc 1, 2, and 3, but it's good to get kind of familiar with it now. So if we want to discuss, oh, and local behavior. If we want to discuss local behavior and end behavior, we need a new function that we call the limit operator. And what the limit operator does is this. It just tells us where the outputs of a function are going as the inputs approach some number or plus or minus infinity. So I very much want you to think of the limit operator as a function itself, and it's a function that takes in another function, and it tells you where those outputs are going as you get close to a number or as you get close to positive or negative infinity. That's what the limit operator does. It says where your function outputs are going, all right? Um, yes, so the limit operator is denoted using this notation here. Let me zoom in. Okay, this is what we call the limit operator. And this means limit as x goes to a of whatever you want to put inside, whatever function you want to put inside f of x, right? So this is the function that's eating another function and telling you where the outputs go, all right? A could be any real number, or it could be plus or minus infinity. A lot of times we want to know what is the limit as a function goes to infinity, or as the inputs of a function go to infinity. Where does that function go, like the outputs? Do the outputs go up forever? Do they go down forever? Do they never settle anywhere? Do they keep bouncing back and forth forever? Maybe they go to a number. Maybe as x goes to infinity, the outputs start to approach 2 or something like that. That's what this thing is going to tell us. It's telling us where things are going, okay? Where things are going. So now we have a bunch of definitions that are really just notation, okay? Really just notation definitions. I'm not going to read all of it word for word, but you're welcome to read it word for word. You should at least a few times, but I'm going to give you the gist of what it means. I'll do the first one and then kind of gloss over the others. So if the outputs of f of x get larger and larger as x gets larger and larger in the positive direction, then we say the limit of f of x as x goes to infinity is positive infinity. And we write this. So let me zoom in for a second. Okay, when you see this symbol, it means as x goes to infinity, f of x goes to infinity. This is the end behavior. So here, this function is telling us the end behavior of f of x when x gets infinitely large. So as you keep going out farther and farther that way, the outputs of your function are going up, 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 up forever. That's what this means, okay? So we use this symbol to represent that behavior. We can also just write this. Sometimes we will write f of x goes to positive infinity as x goes to positive infinity. So these are equivalent. This is the same as writing that. And that's what it means, okay? And that's really what the limit operator tells you. And now we can take the limit going to different places. The results can be different. All of that is fair game. All that is up for grabs. This one down here, limit as x goes to infinity of f of x is negative infinity. That means as x gets larger and larger and larger, your function is getting smaller, lower, 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 going down like that, right? That's what that means, just like that, okay? Now we can talk about going to negative infinity instead. So this one right here, as x goes to negative infinity, our function goes to positive infinity, the outputs. So as x gets larger and larger negatively, our function is going up, 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 all the way up to positive infinity. Then similarly, negative infinity. As x gets larger in the negative direction, our function values are going down, 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 down. That's what that means. And that's it. That's how the notation works, all right? Let's look at some examples. Let's look at a couple polynomials here. Maybe I need to switch to this. Let me do this one first. So here's an example of a polynomial. And what you can see here is that as x goes to negative infinity, the outputs, f of x, are going to positive infinity. And this is the way we write that. The limit as x goes to negative infinity of f of x is positive infinity. And then as x goes to negative infinity, f of x goes to, I'm sorry, as x goes to positive infinity, f of x goes to negative infinity. So this is like the global behavior of these polynomials, the end behavior. Okay, this one, things are switched, right? This is a polynomial where as x goes to negative infinity is over here, f of x is going down, so it's going to negative infinity. As x goes to positive infinity, right? Positive infinity is out there. F of x is going up to positive infinity. Okay, let's look at this one. Here, this one, again, the degree of this polynomial is even because it's going up on both sides. The end behavior is the same as some even powered power function, right? So here, as x goes to negative infinity, f of x goes up to positive infinity. Here, as x goes to positive infinity, f of x goes up to positive infinity, going up like this, right? Same thing over here, except now instead of going up, it's going down. So as x goes to negative infinity, f of x goes down to negative infinity. Here, as x goes to positive infinity, f of x goes down to negative infinity. And that's it, right? So these basically categorize all the different possibilities for end behavior of a polynomial. Let me go back to this. So you only have a few options, right? And it's categorized very nicely. If the degree of your polynomial is odd, it's got to look like one of these. So basically it's like that or like that. If the degree is odd, it's like that or like that. There you go. Odd degree. If the degree is even, it's this or this. Even degree. Just even degree. The actual exponent could be any even number, even like 1,000,002. It could be anything, all right? Okay, so let's compare these two forms. We've talked about local behavior, and now we've talked about global or end behavior, and the different forms of a polynomial give us information about those things, right? So the standard form immediately tells us about the end behavior because the end behavior of a polynomial is going to be asymptotically equivalent to this, right? The dominating term. So when we have the standard form, we can already tell that the polynomial is going to look like this, or this, or this, or this, just at a glance. The factored form is nice if we want to know local behavior. I want to know things like what's happening at all the zeros. These are all the zeros. The notation gets a little messy here, but don't worry, just kind of follow your nose. This is a zero, this is a zero, this is a zero. This is the multiplicity associated with that zero. This is the multiplicity associated with that zero. This is the multiplicity associated with that zero. So the factored form tells us everything we need to know about the zeros and whether we're going to get a bounce or whether we're going to get a cross, whether it's going to look like that, or sorry, look like that. That's what it's telling us, okay? So standard form gives you info about the end behavior. Factored form gives you information about the local behavior, okay? All right, now that being said, let's try to go backward. We've done a bunch of examples where we looked at an expression, a function, now, and then drew the graph or looked at the graph. Now let's go backward. Let's look at a graph and see if we can come up with some possible formula for this polynomial. And I do want you to try this one on your own, kind of working in reverse, but I think you'll be able to do it, okay? So try to deduce a polynomial given this graph. And I want you just to use the smallest degree possible, okay? So think about it for a sec, right? Now, as always, got to say something out loud, right? Now, try to work it out on your own. The hint I will give you is look at the zeros and look at the end behavior. Now, let's do it together. Let's see. Okay, first thing I notice are the zeros. I've got a zero here, a zero here, a zero here. Because I know those zeros, I immediately get the factored form. So just looking at that at a glance, I already know it's got to look something like this. A times x plus 2, x minus 0, x minus 3. Now, the next thing I'm going to do is look at the multiplicities of those zeros. So here, the multiplicity here, or I'm sorry, it's crossing, right? The graph is crossing. So that means the multiplicity has to be odd. And we were told to choose the smallest degree possible. So the multiplicity here is going to be 1. Looks like it's crossing here as well. So the multiplicity is going to be 1 again. And then here we're getting a bounce. We're getting a bounce. So multiplicity 2. Right? Multiplicity 2. So just at a glance, I've already got this. I know that my polynomial has to look something like that. Now all that's missing is the leading coefficient a, and that is precisely why we have this other point. This other point here is the information we need to solve for a. Let me change slides. This just encompasses everything I was saying right here. The zeros with their multiplicities, just like that. And so this is what I had just written a second ago, simplified and shifted around a little bit. This x right here is equal to x minus 0. Now to find a, we plug in this point, 1 comma 6, and we'll be able to solve for a. So our output is 6. Our input is 1. Go through and calculate that out. 6 equals 12a, so a equals 1/2. And so voila, that is the formula for that polynomial in smallest degree. Again, the degree could be larger because we can't actually see directly what the degree is, but we chose the lowest multiplicity possible for each root. So that means the degree is as low as we can get it. All right. And on that note, let's play. Whew. Whew. Oh man, that's a long one, right? I know that's a ton of information. Thank you all for bearing with it. That's a lot to learn all at once. So please do ask questions. We will work on this during the activity. I'm always excited to work with you about this stuff. I hope you appreciated some of the motivation for why. Again, this is a lot to be required to know, right? You know what I mean? Why do we care? The Weierstrass approximation theorem. Polynomials, they just have so many nice properties, right? That's why we study them, because they're really nice, they're factorable, they're nice, okay? So thank you again for watching, and I will see you next time when we talk about complex numbers. Have a good one, everybody.